Unit 1A, Part 2, Polynomial Functions. So this is the second half of the first half of Unit 1, which is polynomial and rational functions. In the first half of Unit 1, we focused on prerequisite materials. In the first half of Unit 1, Part A, we focused on prerequisite skills like factoring and graph analysis. In the second half of Unit 1, Part A, we're going to focus on polynomials and behavior of polynomials. Unit 1, Part B will focus on rational functions. But in order to work with rational functions, we have to have a strong understanding of polynomials. And in order to work with polynomials, we need to have a strong understanding of graph analysis and factoring. So these are the topics that we're going to look at. We've already looked at each one of these topics previously in Algebra 2, but just like in the last unit, we're going to be going a little bit more rigorous, using a lot more calculus-based vocabulary. Looks like we're aiming for a test in the end of September. So today's lesson is 1A.9, Polynomials of Higher Degree. Now, before we jump into this, though, let's go ahead and start with some Bellwork. So some review questions, two factoring questions, and then a solve question. Go ahead and pause here, play when you're ready. So we are going to start with factoring. Notice that on this one, we have a fourth degree term, a third degree term, a second degree term. I have three terms, but all the terms have a variable, so I'm always going to start with GCF. There's no GCF, or at least the GCF between the coefficients would just be 1, so I don't have anything to worry about. The GCF between the variables would be x squared. If I pull an x squared off of this term, I'm going to be left with 6x squared. If I pull an x squared off of this term, I'm going to be left with negative x. If I pull an x squared off of this term, I'm going to be left with negative 2. We're not done until we're done, though. I can look at the remaining polynomial. I see three terms. It's of a quadratic form, so we can try the AC method. A times C would be negative 12. Factors of negative 12 that add to negative 1 in the middle, that would be negative 4, positive 3. So I can take my trinomial, break it into two binomials. X squared is going to become x and x. The 6, I don't know where to put, so I'm just going to put it in both places as a placeholder, and then negative 4 and positive 3 here and here. I look to see if I can reduce anything. I see 6x minus 4 can be divided by 2, and 6x plus 3 can be divided by 3. Don't forget the GCF, which was x squared, should be up front. Final answer. For the problem over here, I'm just going to use the GCF technique. I see that I have a leading negative, so I'm going to pull out a negative. 5 and 20, I can pull out a 5. X cubed and x, I can pull out an x. Pulling out negative 5x off of negative 5x cubed is going to leave x squared. Pulling negative 5x off of 20x is going to be minus 4. I'm not done until I'm done. I see a difference of squares, so let's keep going. Negative 5x, x plus 2, x minus 2. Final answer. Lastly, question 3. This one, the question says solve. I'm looking for something different when I'm factoring versus when I'm solving. Answer the question that's being asked. If I want to solve, there are different techniques that I can use for solving. One thing I need to recognize is what kind of function am I solving? I see this as 2x squared. I have a quadratic. If I'm solving a quadratic, I can either isolate or I can factor. Isolating would be moving terms back and forth until the x is by itself. I use inverse operations. For instance, if I see 2x, I can divide both sides by 2. If I see plus 4, I can subtract 4 from both sides. Isolation is a technique for isolating a single variable. Factoring is for when I have more than just a single variable in the problem, and isolation techniques are insufficient. In this problem, I see x squared and x in the same problem. When I have just x squared, if it was just a single variable problem, isolate. One variable, isolate. Multiple variables in the same problem, my first thought should be to factor. Now, if I'm factoring, I need to set everything equal to 0. That's not a requirement for isolation, but factoring, everything must be equal to 0 before I start. So if I'm going to set everything to 0, I need to get rid of this x. I need to get rid of that 1. If I subtract x and add 1 to both sides, I'm left with 2x squared plus 18 equals 0. Now I have this problem, but notice that there's only a single variable in this problem, so this just became an isolation problem. If it's an isolation problem, I don't need factoring. It doesn't actually need to be set equal to 0. Let's just use inverse operations in order to get x by itself. So I'm going to subtract 18. I'm going to divide by 2. And then to get rid of the square, I'm going to take the square root. Keep in mind the square root of a negative number is going to be I. The square root of 9 is 3, and there's always two answers to a square root, so plus or minus 3i, final answer. All right, now that we've warmed up a little bit, let's go ahead and proceed back to our main lesson, polynomials of higher degree. Let's start with the basic structure of a polynomial. The form of a polynomial function in one variable x is an expression of the form a sub 0 x to the n plus a sub 1 x to the n minus 1 plus so on and so forth, following that same pattern. Now, the pattern here is that we have every term contains a variable, x to the n minus 1, all the way down to x squared, x. This one, technically, there's a variable x to the 0, but anything to the 0 is 1, so we don't have to write it there. And there's a coefficient. A sub 0 is the 0th coefficient, a sub 1 is the first coefficient, a sub 2, a sub 3, a sub 4, all the way up to a sub n. Notice this says a sub n minus 1. That just means the term right before a sub n. So this is a sub n minus 1, a sub n minus 2, and so on and so forth until I get down to 0. Notice this n matches this n, because if this was, for instance, 4x squared plus 5x minus 3, that's a 3. What I would be communicating here is that a sub n, which is this term, would be a sub 2. This would be a sub 1. This would be a sub 0. Just like this is n equals 2. This is n equals 1. And there's an invisible n equals 0 right here. So this is just formatting on how an algebraic mathematician would notate everything as generic as possible. The idea being that a sub 0, a sub 1, a sub 2, those are called coefficients, all the way up to a sub n. So if it's a 10th degree polynomial, there are 0 to 10. There are technically 11 terms if we count a sub 0 as the 0th. A sub 10 would be the last one, a sub 0, a sub 1, a sub 2, a sub 3, all the way up to a sub 10. There would be 10 terms. Those would be the coefficients. And then n is the degree. Whatever the largest exponent is, that's the degree of the polynomial. And the degree has to be a non-negative integer. In other words, I can't have 4x to the negative 1/2 plus 5x plus 2. This is not a polynomial because we have a non-negative integer as one of my exponents. If it was positive, still not a polynomial because it needs to be an integer. I can have x squared, but I can't have x to the negative 2. Not a polynomial, polynomial. Not a polynomial, polynomial. So if there are any negative exponents or rational exponents, then I do not have a polynomial. General shape of a polynomial. When I go to graph a polynomial function, I always get the same basic shape. Consider if I have y equals x, this would be a first degree polynomial or a linear function, and I get the graph of a line. If I have y equals x squared, I have a second degree polynomial or a parabola. If I have x to the third, I have a third degree polynomial, or we don't really have a name for this shape, kind of an S-curve sort of thing. But if I start adding in extra terms, I start to get a shape that looks like a more exaggerated S-curve. And no matter what I do, as I change the value of the coefficients, it's always going to be this S-type curve. No matter what I change here, I might get a simpler version of the curve, but a cubic always looks like this basic S-type curve. So I can predict in advance that if I have a cubic function, I know exactly what that cubic function is going to look like. Notice if I have a fourth degree polynomial, start to move the numbers around. Here we go. Actually, let's add in another term here. Let's do here we go. There we go. So with a fourth degree, notice that the left side and right side go up, but I have a bounce in the middle. It goes down and then up and then down and then back up. I kind of get a W shape. So in general, I can predict what the basic shape of a graph is going to look like based on what kind of polynomial it is. First degree is always a line. X to the first is always a line. X to the second is always a parabola. X to the third is going to be this S shape. Now, the simpler the third, the fewer terms that you have, the less complicated it is. I can have a much simpler cubic graph that's going to look like this, but I can have a more general cubic graph where the left side shifts up, the right side stretches down, and I get this nice S curve. Fourth degree is always going to be this W-shaped graph, but if I have something simpler, a fourth degree could look like a second degree. But here's a second degree curve. If I compare this to a fourth degree curve, notice that the fourth degree curve is a little bit flatter. The fourth degree curve is not a parabola. Only the second degree curve can be called a parabola. A fourth degree curve kind of looks like a parabola, but it's a little bit flatter as it goes through the x-intercept. Notice sixth degree gets even flatter, 10th degree gets even flatter. Keep in mind, it's not exactly flat. If I zoom in far enough, I will see a little bit of distance between the curve and the x-axis, but I'm having a little trouble getting it to zoom in close enough on this because the numbers are so incredibly small. The idea being that for any even degree function, the left and right side are going to go up, versus if it's an odd degree function. Notice there's my cubic graph, fifth degree, seventh degree, ninth degree. The left and right side are going to go in opposite directions. We're still going to get the same basic shape, but for the simplest parent version of the function, they're all going to look basically the same, but they're going to be flatter as they go through that x-intercept. So in general, if it's an odd degree function, the graph must cross the x-axis at least once. For every odd degree function, I have to cross the x-axis at least once. Keep in mind, if it's a third degree function, I see 3 x-intercepts here, but I could just as easily draw a curve that only crosses once. This is still a third degree polynomial, but it only has one x-intercept. It only crosses the x-axis once. If it's an odd degree function, you must cross the x-axis at least once. You can cross it more than once, but you must cross at least once. If it's an even degree, the graph may or may not cross the x-axis. If I have parabola, for instance, this parabola crosses the x-axis twice, but I could also draw a parabola that never crosses the x-axis. Here's a parabola, second degree polynomial. It's still a parabola, but it never crosses the x-axis. Odd degreed functions always have at least one x-intercept. Even degreed functions may or may not have an x-intercept. Always even number of intercepts. Even degree functions will always have an even number of x-intercepts. So if I have a graph that looks like 1, 2, 3, 4, 5, 6, this has 6 x-intercepts. Alternatively, I could have a situation like this is still a 6-degree graph, but it only has 4 x-intercepts. Or I could do something like this, where it only has 2 x-intercepts. If it's an even degree function, the left and right side will both point up. If it's an even degree function, the left and right side will both point up, and I will always have an even number of x-intercepts. Let's talk about zeros, roots, and x-intercepts, which are 3 ways of saying the same thing. A solution to an equation when y equals 0 is called a zero. So when I refer to the zeros of an equation, or the zeros of a polynomial, or the zeros of a function, what I'm saying is set f of x equal to 0. What does x equal? Those x values are the zeros of that function, or the roots of the polynomial. I'm not talking about root as in a square root. The roots of a polynomial are the solutions of the polynomial, are the zeros of the polynomial. So I generally use the word zeros because it's telling you that the y value is 0. What does x equal? Find the zeros, set the y value to 0, solve for x. The solutions to y equals 0 are called 0. Now, those zeros or roots can be real or imaginary. We saw in the Bellwork where we found the solutions to an equation. Though we had 2 solutions, they were both imaginary. X-intercepts are real roots. So the zeros of a polynomial, the roots of a polynomial, the x-intercepts of a polynomial, they're all basically the same thing. If I ask you to find the zeros of a polynomial, that's any value that makes the function equal to 0. Those values could either be real or imaginary. If I ask you to find the roots of a polynomial, same thing. Set the function equal to 0. The answers could either be real or imaginary. If I ask you to find the x-intercepts of a polynomial, keep in mind an x-intercept is a graph. A graph is real. If I'm asking you for x-intercepts, that means we don't have to worry about imaginary solutions. We only have to worry about real solutions. The fundamental theorem of algebra says that if f of x is a polynomial of degree n greater than or equal to 1, then it has exactly n solutions. All right. If the polynomial is degree n greater than or equal to 1, then f of x has exactly n solutions. Notice this is degree 1. First degree has 1 x-intercept. 1 x-intercept is 1 solution. Second degree has 2 x-intercepts. 2 x-intercepts means 2 solutions. This one is 5th degree. N equals 5, we have 1, 2, 3, 4, 5 x-intercepts. That's 5 solutions. Keep in mind, though, we talked about this guy down here. This one is n equals 6. It has 6 solutions according to the fundamental theorem of algebra. Yet it only has 2 x-intercepts. That means I have 2 real solutions, because real solutions are x-intercepts. X-intercepts are real solutions. But if it's 6th degree, that means it has 6 solutions. 2 of them are real, 4 imaginary. I can look at a graph. As long as I know what the degree is, I can interpret how many real solutions it has, as well as how many imaginary solutions. The graph tells me explicitly where the real solutions are. I cannot tell what the imaginary solutions are just by looking at the graph, but I can tell that it does have imaginary solutions. Moral of the story, the degree of the polynomial is the number of solutions of the polynomial. The degree of the polynomial is the same as the number of solutions of the polynomial. Now, I say n greater than or equal to 1 here because if n equals 0, in other words, y equals 4. Y equals 4 is a horizontal line. The degree is 0 because there's always an invisible x to the 0 on the end. If I have y equals to a constant, you can rewrite that as 4x to the 0. If it was 4 or 7 or negative 13, it really doesn't matter. Slap on an x to the 0, that really says 1. 1 times negative 13 is negative 13. The graph of y equals a number is a horizontal line. It has 0 x-intercepts, it has 0 solutions. So you would think, okay, well, that still holds true. Problem is, what if the function was y equals 0? If the function is y equals 0, It's still 0th degree because it's x to the 0, but it has infinitely many x-intercepts. Every possible value of x is an x-intercept. Y equals 0 has infinite x-intercepts, yet it's degree 0. So we fix this issue with the rule by simply saying, okay, well, this rule is only true for degrees 1 and higher. All right. So in the last unit, when we were talking about factoring techniques, I gave you a short little flow chart on what you could do, what techniques of factoring you should always try. Now, this is still essentially the same flow chart, but it goes a little bit more in depth. First off, the goal isn't to factor. The goal is to solve a polynomial. We need to find zeros, we need to find roots, we need to find solutions, we need to find x-intercepts, and again, this is all for polynomials. Anytime you're solving a polynomial, if you're solving by anything other than isolation, keep in mind, if I give you 2x to the 5th minus 4 equals 7, I don't need any advanced techniques for this. It's a one variable problem, just isolate. Done. All right, my answer is the 5th root of 11 over 2. If it's a single variable problem, I don't need any advanced techniques, just use isolation techniques. But if it's not a simple problem, this is a flowchart that you can use to figure out the solution to that problem. Step 1, set it equal to 0. If you know you're going to need to factor, if it's a multivariable problem, there are multiple variables in the same expression, then it's a factoring problem, or at least factoring is going to be something you're going to attempt. If it's a factoring problem, it needs to be set equal to 0 as your first step. Set it equal to 0 before you start to factor. Once it's set equal to 0, we're ready to start factoring. Well, if we're factoring, pull out the GCF first. Always pull out the GCF first. If we don't pull the GCF out first, we're going to have a bad time. Once we've pulled out the GCF, we need to solve the remaining polynomial. This is where the number of terms is helpful to know. If there are 2 terms, well, then it's already fully factored. Set each factor equal to 0, continue isolating the variable. If there's 3 terms, that's where we try the AC method. Remember that the AC method can apply not just to quadratics, but anything of a quadratic form. Try the AC method. If the AC method doesn't work, try the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. If there are 4 terms, try grouping. If there's more than 4 terms, it's either not factorable or we're going to use a calculator to solve it, and that will be in a future lesson. So once we are done factoring by whatever method of factoring, set each factor equal to 0 and list out your solutions. So here are 3 examples that we're going to look at. I want you to find the zeros algebraically. Pay attention to the word algebraically. If I ask you on a test to solve something algebraically and you just write down x equals the answer, you get no points for that solution because the directions clearly said algebraically. If you just write down answers, I have no idea what technique you used. I cannot confirm whether or not you followed the directions, so you get no points. Make sure you show the work that supports your answer. If I don't tell you to find the zeros algebraically and you say use a calculator to answer the question, which is a technique that we are going to use, then you don't have to show any work. Just write down the answer. But if I say find the zeros algebraically, then your grade is not for the answers, the grade is for the supporting work. So let's look at the first one. You should already know how to do this, so feel free to pause here, hit play when you're ready. So we're going to find the zeros. And remember, according to my flowchart, if I'm looking for zeros, set it equal to 0 and solve. So I'm going to set, this is y, so I'm setting the whole thing equal to 0. That's setting y equal to 0. And now I'm going to look to factor. If I'm factoring, I need to pull out a GCF. I don't see anything in common between the 3 terms, so I'll move on to my next step. There are 3 remaining terms. So we have a possibility of using AC method, but it's only AC if it's of a quadratic form. I see this is 4th degree, 2nd degree, constant term. Remember, a quadratic form is this has to be twice as big as this. 4th degree is twice as big as 2nd degree. We're going to use the AC method. So I'm going to break this into 2 groups. X to the 4th is going to break into x squared and x squared. We're going to do 4 times 9, which is 36. Factors of 36 that add to negative 37, which would be negative 36 and negative 1. Keep in mind the 4 up here has to be accounted for, but I don't know where to put it, so I'll put it in both places. Look to see if there's anything I can reduce. On this one, I can divide by 4. And on this one, I can't divide by anything. So 4x squared minus 1. So this would be my factorization using the AC method. Keep in mind the question wasn't to factor, the question was to solve. So this should still be equal to 0. Now I'm going to notice that x squared minus 9, that's a difference of squares. So I could keep factoring. X plus 3, x minus 3. This is also a difference of squares. 2x plus 1, 2x minus 1. Still equal to 0. Don't forget that. The question is to find the zeros once I have fully factored the problem. Notice I have 1, 2, 3, 4 factors. It's a fourth degree polynomial. I should have 4 linear factors. Each factor is first degree. First degree times first degree times first degree times first degree is fourth degree. So I know I have the appropriate number of factors. Now I just need to list out my answers. Each factor, when I set it equal to 0, x plus 3 equals 0, will produce a solution. So this one would be negative 3. X minus 3, set it equal to 0. X equals positive 3. On this one, I'm going to get negative 1/2. On this one, I'm going to get positive 1/2. The problem was fourth degree. The fundamental theorem of algebra says that if it's a fourth degree, I should have 4 solutions. I have 1, 2, 3, 4 solutions. So I know I have the appropriate number of solutions. Don't do a polynomial problem, and leave off a solution simply because you forgot to count. There are supposed to be 4 solutions. There are 4 solutions. I'm happy. Now, I'm done with this problem, but I do like to point out that this step was not necessary. As soon as I get to this step right here, x squared minus 9, I could recognize, well, x squared minus 9 set it equal to 0. That's an isolation problem. X squared equals 9, and then square root both sides, and I get plus and minus 3. I generally recommend do the factoring technique unless you're sure that you're not going to forget to put both plus and minus on this step. If you fully factor it, each factor has its own solution. If you use this technique, you need to remember that when you take the square root of 9, there is both negative 3 and positive 3 as your answer. Same thing over here. 4x squared minus 1 means 4x squared equals 1. X squared equals 1/4. Take the square root of 1/4. I get positive and negative 1/2. Square root of a fraction just means take the square root of the top number, 1, take the square root of the bottom number, 4, and we get 1/2 and negative 1/2. So either way is fine. Remember, I suggest factoring out completely and then listing out your answers. But if you're confident in yourself, once you've practiced this sufficiently, I see x squared minus 9, I'm just immediately going to write 3 and negative 3. For this one, I'm immediately going to write 1/2 and negative 1/2. Here's another question. Pause here, play when you're ready. All right, so set it equal to 0. Look for a GCF. This time I do see a GCF of negative 2t. That's going to leave behind t squared minus 4t plus 1. Now keep in mind, we're solving now. Once I pull out that GCF, I know that one of my solutions is going to come from that guy. Anytime I have a GCF problem and I pull out that GCF that contains a variable, divide both sides by negative 2, t equals 0. If it's a GCF problem, t equals 0 is going to be one of my solutions. Don't forget to list t equals 0 as one of my solutions. Often we spend so much time factoring the rest of it, we forgot to come back and list t equals 0 as the solution to that exterior factor. But of course, also remember it's third degree. I should have 3 solutions when I'm done. The remaining polynomial up here has 3 terms. I'm going to use the AC method. T squared becomes t and t. There's just a 1 up front, so I don't have to worry about any coefficients on the t's. Factors of 1 that add to negative 4. Factors of 1 that add to negative 4. You're not crazy. There are no factors of 1 that add to negative 4. This is not factorable. Now, the question was not factor. Not factorable is not the answer because the question was not factor it. The question was to find the zeros. We need to solve. Just because it's not factorable does not mean it's not solvable. It's just not solvable by factoring. This is quadratic. I can solve any quadratic equation using the quadratic formula. If it's not factorable, then jump to the quadratic formula. Keep in mind, I could have jumped to the quadratic formula as a first step, but factoring is so much quicker and so much easier than using the quadratic formula. I'm going to save the quadratic formula for when I can't factor. If I can factor, solve by factoring. If I can't factor, let's use the quadratic formula. Recall that the quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. Let's also note that it's not x, it's t on this problem. A is 1, b is negative 4, c is positive 1. That's a 1. All right, so b is negative 4, so negative 4 actually makes it a positive 4. B squared is going to be a positive 16. A and c are both 1. A is still 1. So t equals, that's going to be 4 plus or minus the square root. That's going to be 16 minus 4, which is 12 over 2. All right. Now, if this was factorable, if this problem was factorable, this will be a perfect square. If a problem is factorable, this will be a perfect square. So if you realize that it's not factorable, then this will not be a perfect square. If it's not factorable and I'm doing the quadratic formula, I expect to get something here that is not a perfect square. So the fact that it wasn't factorable and I got a 12 right here, I'm getting exactly what I expected to happen. If this had been a 16 right here, I did something wrong up here. You might want to consider thinking about what you did up there incorrectly, or did you do something down here incorrectly? Not factorable, not a perfect square. Factorable, perfect square. Now we can't leave this radical alone. We need to simplify all of our answers. Keep in mind that the square root of 12 can be broken into a product. The goal when I'm simplifying radicals is think to yourself, what's a perfect square that multiplies into 12? I know 12 is 1 and 12. 1 is not particularly helpful because then I could say this is square root of 1 times square root of 12. Square root of 1 is 1, so square root of 12 is square root of 12. Not particularly helpful. I know it's the same thing as root 2 times root 6, but neither of those are perfect squares, not particularly helpful. What I want is root 4 and root 3. Since 4 is a perfect square and root 4 is really 2, square root of 12 is really equal to 2 root 3. So let's go back up here. I can rewrite this problem as 4 plus or minus 2 root 3 all over 2. I'm not done until I'm done. Notice that in the numerator, I have two terms, 4 and 2 root 3, that both have 2 as a factor. I can split this into two fractions and then reduce each fraction to get my final answer. This would be the fully simplified version of this statement right here. But remember, I'm not done until I'm done. This was a third degree polynomial. There should be 3 answers. I have 2 plus radical 3. I have 2 minus radical 3 as 2 different answers. But let's not forget about 0 as one of my other answers. So 0 would be an answer as well. If I'm solving, always make sure you label t equals, x equals, whatever the variable equals, and then I list out my answers. It's perfectly fine if you just leave it like this. Either one of these answers is perfectly acceptable. Last question. Pause here, play when you're ready. All right, we're finding 0, so set it equal to 0. I see 1, 2, 3, 4 terms, so I'm probably going to use some sort of form of grouping. I also see a clear GCF, 2x squared. That's going to leave me with x cubed minus 5x squared plus 4x minus 20. Notice that I have a GCF out here. I know that x equals 0 is going to be one of my solutions. I'm going to keep factoring. I've got these two guys. I can factor out an x squared and leave behind x minus 5. I need to pull another GCF out of these two, and it needs to leave behind x minus 5. Notice if I pull out 4, it's going to leave x minus 5. So x minus 5 is one of my factors, and x squared plus 4 would be the other factor. Keep in mind 2x squared is also a factor, so if I was asked to give the factorization, this is the complete factorization that I'm now setting equal to 0. And once I have my factors, I can just go through and identify my answers. So I know this one is going to give me x equals 5 as a solution, because set this equal to 0, x minus 5 equals 0, x equals 5. I already know this guy is going to give me x equals 0. If I do that the long way, just to say that I did, setting this factor equal to 0, divide both sides by 2, take the square root on both sides, the square root of 0 is just 0. We don't need to put a plus or minus, it's just 0. So there's 0, there's 5. Now with this guy, remember, this is a sum of squares. This one is not factorable. If I go to solve this off to the side, subtract 4, I get negative 4, take the square root. Square root of a negative 4 is plus and minus for a square root. 2 for the 4, I for the negative. So square root of negative 4 is plus or minus 2i. So I've got plus or minus 2i. Now notice, how many solutions do I have? I got 1. Keep in mind, plus or minus 2i, positive 2i is one answer, negative 2i is one answer. So I have 2 answers here. Notice it's second degree, so I have 2 answers. This one is first degree. I have 1 answer. X equals 0. Remember over here I said we don't need to put plus or minus because it's 0. But technically, it's not just 0, it's 0 twice. X equals 0 represents 2 solutions because that's second degree. So I have 2 solutions here, 1 solution here, there's 2 more solutions right here, 5 total solutions because it was a 5th degree polynomial. Whatever degree the polynomial is, that is exactly how many solutions I expect to find. Once you get to the end, double check, did I find all the solutions that I expected to find? If not, keep hunting, figure out what you missed.